SwayamPrabha. Digital India. Educated India.
So, we have been talking about this plug flow, and I definitely now think that you will not forget about definition of plug flow, then mathematics are required. So, you have that equation 0 to that simplest equation, and I also told you why you should have this plug flow assumption. Why? I told you why you should have plug flow assumption. What will happen if you do not have plug flow assumption?
Each point will not be the same.
Only you are making noise, I want signal.
Very
clearly one.
Diffusion also.
So what? You consider diffusion?
You end up with mathematical complications.
Yeah. Straightforward action, I say. Okay. Yeah. Unnecessarily, you don't have to use your brain for mathematics. When it is required, you have to use it. Right. So, as engineers, you first simplify things so that you will get the simplest design equation. Then you want to complicate. Right. So, that is what is the thing, that is why you have to assume that, and in the beginning, and if you are really a fussy guy, so naturally you will now try to go for deeper and deeper, and then use all terms that you cannot neglect in the real flow, and those are the terms which I am going to write now for plug flow. Plug flow, the actual, it is not plug flow, tubular flow, the actual design expression I will write. We will simply write here still plug flow. Okay, it is a differential equation. I will explain I am not deriving that, but I will give the differential equation. Most of you would have seen this equation, but only thing is we will know what are the terms. I think in the equation you should know what are the terms, which term is representing what phenomena. Equation always comes from physics, please remember that. Okay, physics means you understand physics of the problem, not Resnick and Holiday. Physics means Resnick and Holiday book is there, no, very famous. You have not seen? Oh my God, you are not prepared for JEE? Really? JEE, it is Vedam. You know Vedam? Bible, okay. Okay, so that is why everyone uses it. We say Vedam or Bible or Quran because everyone supposed to use that every day. So that is why, that is the reason only we will say. So this Resnick Holiday, when I say physics of the problem, we are talking about the physical phenomena that is happening. Not physics means immediately our mind should not go to a book. Physics book. That's what physics book you have used?
Standard state boards.
State board. Afterwards, no more extension of physics. Particularly in physics, there are wonderful books. Because physics is a wonderful subject where every day you see. Right? Chemistry you cannot see every day. You feel chemistry every day because in the stomach reactions and all that. Okay. Yeah. And I think you can't see a reaction, even though you have you know that there is some reaction you can't see. But the advantage of the physics is that everything you can see. Okay, so that is why many people try to explain and all that physical phenomena. Okay, and also the physics around the world and the universe. So that is why you have the maximum information on physics, and people are so much excited about physics. The best physicians, and not physicians, I mean physicists. Okay, physicians mean again you go a different way. Yeah, doctors. Right now we don't want to go there. Yeah, so best physicists, Nobel laureates and all that, they started propagating that in very, very simple language. That is why there are many popular books on physics. Why I am telling all this is, if you are able to read those books, your chemical engineering also will be very clear, if you are able to. And sometime you have to read I say. Okay, till at least 25 years, 30 years, I think only you have to read and think about that. Okay, because he has been seeing that physics every day. What happened was, it is Challenger. One spacecraft went into space, and then after 3 minutes or 2 minutes, it exploded and 7-8 people died. Okay, Challenger, no? Challenger, I think, yeah, it was Challenger. So there was a committee to find out what was the actual reason for this explosion. This is very good, this example. Then he was in the committee. And they called all the people who have designed and who have also fabricated and who have operated, all these people, and then finally he only proved that that between they have the first part, I think, is the people who sit there, the first part, and the bottom parts sections, all the fuel is kept at the bottom, okay, either solid fluid or liquid fluid. Solid fluid, I think, what they have used there, okay, or liquid fluid, hydrogen, liquid hydrogen they use, okay. So that fluid is used, different sections. We can also see when our people also send, ISRO people also send, first part will fall first, second part will fall first, third part also will fall first. The third part should not fall, okay. that should go. But anyway, I think I am not joking about ISRO, because I think in every history of any rocket science, it seems everyone has faced these problems. Even Americans also lost many rockets like that when they were trying. So that's why it's only learning curve. So we are on that learning curve. So that's all. That's why. But our people are successful, no? In many things now they are sending, and all these satellite connections and cell phones and these classrooms, various places, all that is through that only. I think we are also doing excellent job in that. So that parts will come in one, and between these two, okay, first part, bottom part I am talking, where the fuel, second part another fuel tank, and maybe depending on how far that goes, maybe third part, fourth part also they will have, right. So in this one, I think between third part and first part, second part, I think, so there was a gasket, O-ring they call. I don't know whether you heard of those things, because when you are joining two metal parts, yeah, these two metal parts will have groove. So okay, like this, oh my god, okay. So here they will have a groove, the other side also they have the another groove, right, and in that groove you put that nice O-ring, circular, this is circular, and the diameter also is circular diameter, that is, yeah, like that, okay, circular. So that they put and then tighten, right. So then what happened was, they found that they know that the reason is the explosion occurred in the hydrogen tank when it is coming to the second stage. First stage has gone, and that has to propagate to the second stage. So when it is going to the second stage, something happened, and then suddenly it broke and explosion occurred and then died. All the people died. I think you can see, two parts it came, and even now they will show in TV sometimes when that the same day when it occurred. That's what I was thinking. There are moving bed reactors, right. I think one beautiful example is, gasifiers can be used as gasification can be conducted in moving bed, not packed beds. So that means the entire bed will be moving. When the entire bed will be moving, depending on slowly, the conditions inside and how much is coming, there will be some gaps between the particles. Those are the gaps which I saw between, there is one group which is talking, another group which is talking, there is a wide edge between that. So throughout that I was thinking, now what should be the wide edge, what should be the porosity. So all that I was thinking, so that's why that's why I enjoy, those kind. I don't get bored, because I am now thinking that okay, all these are particles, they are moving, some with different velocity, some with same velocity, okay, I mean not same velocity, means another velocity. So if all the people are moving with exactly same velocity, plug flow, okay. Yeah, so all that kind of things, if you are able to relate, you will never forget that. So that's why I am trying to tell you all these stories, because by storytelling you will definitely remember, at least few people will change. They don't erase the files immediately the moment they cross the door, okay. You have no delete. After deleting files, computer will tell you have successfully deleted the files. I mean, this is most stupid congratulations I ever seen, that you have not done anything. Computer deleted, it says that you have successfully deleted the files. So that is like that only. Another thing also, Windows, to switch off, to stop the computer, where you have to go? Start. What a wonderful command, okay. To switch off the computer, you have to go to start and then open, find out where is switch off and then switch off that. Okay, that happened because this Bill Gates was not educated. Correct? No, he was not educated, in the sense that he dropped out from some time. Okay, if you could have formal education, that is my addition, probably would have taught where is the correct button. But anyway, so the final expression which we have to use is that dou Ca by dou T, this is unsteady state also. Okay, I think I will write everything together. Minus dA dou square Ca by dou z square minus dr dou square Ca by dou r square plus 1 by r dou Ca by dou r, yeah, plus u dou Ca by dou z equal to minus Ra. Okay. So, this is the real equation for tubular reactors where there is no plug flow, right. So, now this equation is with this is unsteady state, tubular flow, reactor with axial and radial dispersion. Okay. Yeah, what are the units of that equation?
Moles per volume time.
Yeah, moles per,
Volume time.
yeah, for unit volume per unit time. Okay, yeah. So, this you see, can you identify where is the axial dispersion term?
Yeah.
Huh?
Yeah.
I am asking you. You are telling something. You. Yeah, what is your name? Anupriya, yeah. Don't be afraid, I say. Yeah, tell. DR. I am asking axial dispersion now. Where is the axial dispersion? What is the axial direction for us? Z or R? Okay, Z. Okay. So, where is that? Anupriya? dA. That's why I also put A there. Okay. This is diffusivity coefficient in axial direction. And what is this one? Radial direction. Okay, this is a cylindrical coordinate because that is a cylinder, right? So that's why this term will come. Transport phenomena, all of you must have been experts. I think definitely all of you would have taken, no? Transport phenomena, right? Yeah, not taken?
Second.
I am talking about BTech.
Yes, sir.
Flashback. Don't forget your past, I say. Yeah. Otherwise, I will tell you like this. Every movie tells you, yeah, like this, there is a flashback. Okay? Okay, good. So, this is the one radial dispersion, and this one?
Diffusion.
U dCA by dz.
Convection.
Convection term. And this is the one? This one? Unsteady state. So now, actually, in reaction engineering, what are the terms we have used from this equation? In our class, when we are deriving that equation, V by Fa naught equal to dxa by minus Ra and all that. So what is the equation I have used? I mean, what are the terms I have taken from this equation? Huh? Minus Ra alone, huh? If minus Ra alone, where do I put it? I say? Huh? You check my notes. I mean, is it dCA by dt?
No, U into those either level.
Yeah, with convection and
Convection.
I told you all reaction engineers are steady state people. Correct, no? I told that. Now, where is convection term there? Okay, this term. Okay. So, out of all these terms, how many terms we have taken? And what are those terms?
One minus R.
Minus Ra and?
U dCA by
That's all, only those two.
No.
That's all. Really, only those two. You see how much simplification we have done. So we said that unsteady state I am not bothered because I am only steady state guy. Okay, so this term has gone. So by plug flow assumption, you have been telling all the time that axial mixing equal to 0 without understanding why. Okay, so when axial mixing equal to 0 means dA equal to 0, right? So then what is the radial mixing? Infinity. So this is infinity. So I cannot put infinities in the equation. So then how can I eliminate this term?
Maybe we can put
Good question.
Can put dr is equal to 1.
Huh? Well, question also I have to appreciate myself. Yeah. You see, we said infinite diffusion. Infinities you cannot put in any equation. You cannot solve them.
R tends to 0.
R tends to R.
R tends to 0 means there is no reactor. Very happy. Correct? No. When R tends to 0, where is the reactor? Reactor disappear.
Dou CA is 0. Dou CA is 0.
Yes. Dou CA by dou R is 0. Gradient is 0. Because it is uniform, no throughout. Where is the gradient? See, those things I say, please try to sharpen your brain. Gopinath. Okay, go to central workshop, take a file, okay, open your brain and then sharpen. Okay, so otherwise I think it's not happening. So many things I am telling you, but I think still it's not sharpened. You are not yet caught the that ignition point. Okay, so I want to see some ignition in the minds. Okay, you see now this is the very general expression, and teaching wise also I can tell you. Highly mathematical people, there are very large number of professors who are very happy writing the equations on the board. Okay, so they are not wrong because their approach is different, and engineers approach may be different. Okay, I mean practical people approach may be different. So what I do is I take whatever is necessary and we write the balance equations. That is one way. Whatever is necessary for plug flow, we said that by assumption there is no axial mixing, the radial mixing equal to infinity and flat velocity profile, these two also enough. Okay, and of course all the time taken by each and every particle is same. All that assumptions will tell me that you don't have axial mixing, you don't have radial, you have infinite radial mixing. So these two terms I drop and then I write only this equation, simply what is entering, what is leaving, and then we write and develop the equation. That is one way of approach. The other way of approaching is that you take the most general expression, take all non-idealities into account. Okay, so then you now develop and write an equation. This is that kind of equation where all the terms we have taken, all the phenomena that is happening in the tubular reactor we have taken, right? We have taken that we have axial mixing, we have taken that we also have radial non-uniformity. That means it is not infinite. Okay, there is some change with the change in the conversion along the radius. You know when that can happen? It can happen in packed beds. And I told you all packed beds can be imagined first approximation as plug flow. Why? Flat velocity profile. What is the kind of velocity profile you will get in a packed bed? So I have packing here. Okay, I am sending reactor there, it is coming out. This is packed bed. Yeah. So when it is entering, we assume that it is entering state as it is, entering by plug flow. That means before that I have uniform velocity profile, and there are many assumptions like this is only academician way of representing the packed bed, but in reality you will never have packed bed like this. So you will have a pipe like that, right? If you have a pipe, then all this will go because it has to expand slowly, So that is why before putting all this into the packed bed, you just draw here itself cone, right? Your actual reaction should start from here. Why you are doing all this? I am doing all that so that I can easily quantify in terms of mathematical equations. So if I do that, then it approaches almost this plug flow, and from there it moves as plug flow. The velocity profile is assumed most of the time like this, and again you have to use here high Reynolds numbers. What are the high Reynolds numbers for turbulent region in packed bed? 500 and above. If you do that, then you will get almost flat velocity profile, and in packed beds you can easily get this. That is why at low Reynolds numbers itself you are able to get that, because there will be small fluctuations, that is later, right? So because this kind of uniformity will come because of this solid's presence. when you have the solids, those things will try to balance the flow. Somewhere here it goes faster, somewhere it goes slower, but on the average again that goes faster, this goes slower. So, if you look at that, on the average you have only flat velocity profile. Okay, flat velocity, that is our assumption at the end. So, that is why please remember all packed beds are imagined as packed bed reactors. That is the first assumption, right. Then if you say that okay, no, I do not want to take only ideal plug flow, so I want to take axial mixing, that is the first non-ideality. Ideal mixing is a non-ideality because ideality will simplify my equations. Okay, good, that is the one. So, then second one is radial. Radial can occur here because you know any reactor or any reaction reaction will be either exothermic or endothermic. So, imagine that I have the exothermic reaction, easy to remember, hot means easy to remember. Okay. So, then I will put a jacket outside this, then of course it enters and then comes out, right. So, then it is an exothermic reaction, throughout the bed the reaction is taking place, right. So, then when reaction is taking place throughout the bed, then you will have now temperature maximum where, and you are removing heat continuously. Yeah, at the walls you will have, yeah, at the center you will have maximum temperature, and at the walls you have, yeah, some temperature which is which depends on the coolant and all that. So, that is why now you have a temperature gradient, at the center you have more and at the wall you have less. So, temperature gradient is there. So, whenever you have the temperature gradient, now concentration gradient also comes into picture, correct, no? How? Because you have if it gas phase reaction, how do you calculate concentration? I have a gas phase reaction, I know only pressures, partial pressure divided by R into T. Now, the temperature is changed. At the center you have high temperature, that means you will have low concentration, and at the wall you will have low temperature, that means you have high concentration, that means there is a concentration gradient which is not allowed for ideal plug flow. So, that has to be taken into account if you are really worried about that kind, because I think in packed beds you have to really worry about that. You know the size of the packed beds in industry, it starts with maybe 1.5 foot feet, right, 1.5, 2, 3, and it can go to even 5 foot means 5 feet, 5 feet means maybe okay, 6 feet means 2 meters. Okay. So, then you can imagine how much that. So, that big diameter packed beds. So, that is why heat removal also is a biggest problem in packed beds. You cannot put only outside jacket, sometimes you have to put also inside heat removal systems, inside here like this. So, all this will disturb the flow, right. So, that is why the real expression what you have to use, and when you are also studying the first time, then unsteady state also will come into picture. You have to solve this equation, and then you have to find out when the steady state comes. Like most of the process control graphs will be with the time and variable. How it go? It goes like this, like this, like this, like this, like this. That is what is steady state. Okay. So, we are not bothered about all that, we are only bothered about that particular thing. You have seen many times response curves. How the response curves will be? Always it goes up, goes like this, goes like this. Sometimes it goes shoots up like this, like this, like this, goes like that. Okay. So, that is why for starting point you also should have this term, this term, this term, and all other terms you should have, and then you have to solve. That is what is the most difficult expression. It is not that easy to solve. Okay. So, you do not have an analytical solution for even first order reaction there, right. You have to go for some numerical technique where you have to use delta R here, delta Z here, delta CA, delta T. So, finite difference methods, various methods are there, you can always see. You see, I mean how complicated the reactor design expression the moment I go to the real world. That is why I want to be in Leonspiegel's world. Leonspiegel's world is imaginary world, beautiful, very simple problems and also very nicely done, and with jokes and all that. So, but the real problems you will see in Smith book, James Smith, Chemical Engineering Kinetics. Particularly if you see the last few chapters, 13th chapter I think, 14th chapter is non-catalytic reactions, 13th chapter if you see, you will definitely see wonderful problems solved by him, one dimension, this is two dimensional, this is two dimensional, okay, that is axial direction and also radial direction. He has really solved the examples. All this of course we will discuss more in chemical reactor, chemical and catalytic reaction engineering next semester. Okay, good. So this is what is about the packed bed reactors, and yeah,
minus area, sir, minus of minus area.
It's just minus area only.
Means KCA.
No,
In place of minus area, if it is a first order reaction, KCA.
it will be case.
No, sir. Minus KCA.
Sign problem.
Yes.
Okay, that you can take care of when you are writing for
Reactants or products.
when you are writing for which component. Okay, yeah, that's okay. I mean that minus sign you can take care of that properly when you are writing for either reactant or product. So that is not a problem. Okay. So, but only thing is you have to see that correctly what are the other terms that are there, and you have to also bother about sign, because you can also realize that when you use wrong equation, concentration will be increasing instead of decreasing. Correct, no? Because if you mistake that, so then I think you can really check. But I do not think any student, as far as I know, has solved this equation using all the terms. Do you know anyone who solved? I do not think. MTech also who is solved? MTech only we are talking. Okay, I do not think. Do you think BTech? I think we are telling this. Project we do not know. I think project also I do not know anyone who has done it. In fact, that is what I am trying to say. Okay, so that is what, this is also a good project for you where you have tremendous learning. Good mathematics you have to use, good physics you have to use, and then you have to calculate. What do you calculate? Concentration, if it is isothermal reaction, and if it is non-isothermal, then similar equation exactly will come for temperature. So concentration profile and temperature profile, that is what Smith has solved in that book, temperature profile and concentration profile. Okay, transport phenomena approach, this is just nothing but transport phenomena approach, and even transport phenomena also I do not think anyone will talk about this equation so much, because this mass transfer reactions coming in the last chapter, no. So by the time you come there you are already tired, because this momentum transfer and heat transfer will kill you. So I think only first chapter you do, and then you read other things, you never read anyway. So that is how I think transport phenomena also we do not go deeper, right. Good, anyway, so that is the one, and I have also not given the actual graph for that equation. V by F naught equal to 0 to xa dxa by minus Ra, right. So this is what we are plotting. So you can tell me how we have to plot. This is xa, this is 1 by minus Ra. Please make a habit of immediately marking x and y coordinates. What is that? Simply do not draw two lines and then draw the curve, right. I mean that should go to you into your blood as engineers, not only engineers, anyone has to do that. Initial conversion 0, yeah. First I have to draw 1 by minus Ra versus xa, right. So initially minus Ra into Kca, K into C, first order if I take for example, K into Ca naught is or Ca naught square if it is second order reaction, then I will have some value, it is not 0, right. Yeah, so somewhere it starts here, and then finally when R is 0, that should happen when I have 99% conversion, almost it is going to 0, so it goes. So in between it may go like this, but this is not the universal shape I am drawing there. Actual first order, half order, and also 0th order, all that you can plot, you will get slightly different curves, right. So general curve only I am drawing. So x f I am just showing, that is what my conversion is, 90% conversion for example. So then area under the curve will be, yeah, in fact I just plotted only this side. It is our elementary calculus which we learnt in school, and probably we have forgotten also in school, right. But here we are using that, elementary calculus, y dx. This is nothing but y dx. Y dx means we will remember, correct? No, integral y dx is area. This 1 by minus r a is y for me. So that simply becomes y dx, right? So that is area under the curve. This will give me v by f a naught. Okay. So then if it is a new reactor, I should assume what is XAF, correct? No, for a new reactor, you are designing a new reactor. So then you have to calculate volume. That means you draw a line, because XAF you know, XAF you know, you assume 90%, draw a line and then count the area. If you are doing simply graphical integration, then that will give you v by f a naught. What do you do if I have the volume already and then I want to find out conversion? What do you do? I know the volume, I have 1 meter cube. What is the conversion? How do I use this graph? Why so much time? Gopi, tell us.
Trial and error.
Where is the concentration? We are talking about the same graph. We are not redrawing any other graph at all. That.
Just have to find out constant.
Because these are the things which you are going to do when I give the assignment. Anyway, I think this Moodle and all that, I think it depends on its mood and my mood. So these moods are not matching. So that's why I think please collect all that and we will go to the plug flow assumption, simple assumptions, and then I think we will go. I will upload whatever I want, because that is only for high funda people like Ranganathan. Okay. Yeah, it is simple for me. If you, I think collect already, many people have given. No, please give your emails. Yeah, and when I really become expert in Moodle, then I will tell you. You also go and see Moodle, okay, because I am not my restricted every time. I don't have that much time to learn. Also, if I have that much time, I will learn. MTech all added. Otherwise, there is another simple. I cannot, because I think yes mail will go to all the people throughout the institute. So maybe I think yes mail for MS. I mean for chemical separate. Do you have only for CHE? I don't know. Anyway, okay. So, but here what we do is we now start counting the area first. So V by F A naught I know, because 1 meter cubed I know, divided by F A naught I know, because F A naught is input for us. Then you start counting the number of that area, number of squares, and then finally whenever you are getting this value, draw the line, that is the conversion. And that you have to do anyway when you are not able to integrate analytically, or otherwise you can go for some other numerical technique. So these are the things which you have to, and now you have to stop. Yeah, there are some applications also for this plug flow reactor. Applications in the sense that I want to give you some real life examples like thermal cracking of hydrocarbons quickly. That reactions conducted in PFR, that you write. Reactions conducted in PFR, because then you will also have a feel that we are not talking just like that, right? Reactions conducted in PFR, just below that what you write, homogeneous reactions. Homogeneous reactions, you would have heard of these things, but I think probably you may not know this. Thermal cracking of hydrocarbons to ethylene, that is one. Thermal cracking of hydrocarbons to ethylene. You know ethylene, no? Yeah. What do you get? Ethylene you are producing. What is the use of ethylene? Polymerization. Okay. Yeah. So that is what I think you also should know what is the use of that. Okay. Second one is oxidation of nitric oxide. You know why oxidation of nitric oxide is done? One of the steps. All gas, homogeneous reaction. Yeah, this step comes for producing nitric acid. That is intermediate step for nitric acid. And incidentally, this is the only third order reaction example. Okay, I don't know other reactions, but this is one of the, if someone asks you in interview what is the third order, because third orders are not many. Okay, first orders are many, second orders are many, third orders are not many. But if someone asks you, because it is not many, people may ask, what is the third order reaction, can you give an example? This one, this goes straight to stoichiometry. This is 2 moles, this is 1 mole, 2, 1, third order. With respect to this, second order, with respect to this, first order, third order reaction. Okay. So, I think this step comes in HNO3 production. Next one, sulfonation of olefins. Olefins, what are olefins? You remember? Organic. So, that is why chemistry, Gopinath, we should have. When we studied 5 chemistries. Organic 1, organic 2, inorganic 1, inorganic 2, and general chemistry. Physical chemistry, later I think totally till 3 years we have studied, 6 semesters. At that time it is 5 years course. Yeah, around 6 semesters we have studied. So, I mean, doesn't mean that we remember everything, but that much chemistry exposure is there, I think you will really appreciate chemical engineering. Right? What is olefins? Double bond things. Alkenes also can be called as olefins.
No.
Yeah. So CN to CN
H2N.
H2N. CN H2N. Okay. For olefins. Cracking of them. Sorry, it's not cracking. Sulfonation. Sulfonation. What for we do sulfonation? Detergents. Soap. Exactly. Detergents. So that's why for every reaction we have some use. But unfortunately, we are not telling you. You are also not bothered to know. Okay. Good. That is one. So next one is fourth one, decomposition of acetaldehyde. Decomposition of acetaldehyde. The reaction is CH3 gas, sorry, CH3 CHO gas giving us CH4 gas plus CO gas. CO gas. So, to get methane, for example, acetaldehyde decomposition, okay, and CO also. Yeah, then phosphine decomposition. You heard of this reaction? Phosphine decomposition. Phosphine. Oh, I think getting late now. Phosphine decomposition. So, that is 4PH3 gas giving us P4 gas plus 6H2, sorry 6H2 gas. You know the beauty of the reaction, 4 moles giving 7 moles. So, disaster if you put this in a plug flow reactor, expansion is too much, yeah. So, then here beautifully it comes what is T bar, mean residence time, and what is tau, all that will come here. So, these are homogeneous reactions. For heterogeneous reaction, sulfur dioxide oxidation, ammonia synthesis and sulfur dioxide oxidation. Okay, these two are enough.